Hello, Frank, do you hear me?
Yeah, sure.
Yeah.
Is this Clément?
Yes.
Oh, okay, good. So I think the first paper is my paper, so you should share it, I guess, right?
Yeah, of course.
Okay.
Welcome, yeah.
And I think it's better if you kind of animate the session. So I will be here in case of trouble or if there are other questions. But I think we don't have any feedback of the audience somehow because we just see the screen remotely. So we don't see how crowded is the room and whether there are some questions.
Yeah, of course, I will animate the questions. Don't worry.
Okay.
So, welcome all to the computational information geometry session, first session actually. And so, we begin with a talk by Frank Nielsen of Sony Computer Science Laboratory and Richard Nock about computing statistical divergences with sigma points. Okay.
Computing statistical divergences with sigma points. This is a joint work by Frank Nielsen from Sony Computer Science Laboratories and Richard Nock. So the Kullback-Leibler divergence is a separated measure of distortion between two densities P and Q defined by this definite integral formula. This formula can also be expressed as the expectation with respect to P of a log density ratio. So the Kullback-Leibler divergence is also known as a relative entropy because you can express it as a cross entropy, which is this formula, minus the entropy, which is a self entropy. And you find this formula again. So the KLD is some measure of between densities, which is asymmetric, meaning that KLD of P to Q is different from KLD from Q to P. And because the integral can be finite or infinite, it might not be bounded. Okay, so for example, if you take the KLD between the standard Cauchy density and the standard normal density, you find that it is plus infinity. So depending on the density P and Q, it can be very tricky to compute KLD in closed form because you have to compute this integral here for continuous densities, or you have to compute some infinite summation if you have a probability mass function, like for example, if you consider a Poisson or zeta distribution. So in practice, when you don't have a closed form solution, what you do is you estimate the KLD quantity by some Monte Carlo stochastic integration. So that means that you're going to take x1 to xm, which are IID samples from P of x, and you're going to replace this integral by a sum where you divide by a P of xi. So you will find that this is the average for m of the log of a density ratio at the sample points. And a good property of this Monte Carlo stochastic sampling is that the estimator is consistent in the sense that when you take the number of samples bigger and bigger and tending to infinity, then you will find the real value of the KLD under mild condition. So the KLD is one instance of a more general class of distortion measures that are called F divergences. If you take a convex generator F of U, you can define the F divergence between P and Q by this formula. And if you take minus log of U here, you will find the KLD formula, okay? The important point is that KLD and F divergence are separable divergence in the sense that you can express it as an integral of some scalar divergence quantity, okay? And the definition of sigma points is that you are going to replace this separable statistical divergence by a summation here. You are going to sum at some special value, which are called sigma points, by analogy to the scented transform in signal processing. And if you have this equality for S sigma points, then you will say that you have a sigma point expression of your statistical divergence. Okay, so let's try to do it for exponential family and KLD. So I recall the definition of a natural exponential family here. It's a parametric family of distribution which can be canonically expressed like that, the density. And F here is some function that is called the cumulative function expressed by this quantity, and it is used to normalize the distribution to 1. So actually, if you take a lot of common distribution that we use in probability, like Gaussian family, beta or gamma, Dirichlet, and so on, they are exponential family once you express the usual ordinary parameterization into the natural parameter parameterization. Okay, and exponential family admits some dual parameterization that we call the mean or moment parameterization, which is written here by eta, which is the expectation of the sufficient statistics, and which can be shown to be equal to the gradient of the cumulant. Okay. So now it's very well known that the KLD between two densities of a same exponential family equals a reverse Bregman divergence. So the reverse Bregman divergence is just the Bregman divergence for swap parameters here. Okay, this is a very standard result. And the Bregman divergence is defined for a strictly convex and differentiable function by this quantity. If you use mixed parameterization of natural parameter and moment parameter, then you get an alternative definition for the Bregman divergence, which is called the Legendre-Fenchel divergence, and which is given by this expression here. Okay, so here we have the natural parameter expression, and here we have the mixed parameterization for the Legendre-Fenchel divergence. And actually, this formula can be extended when you want to compute the KLD between two different exponential families or two densities of two different exponential families by this formula here. So I refer you to this recent work here for a derivation of that formula. So now, to express the KLD between two densities of an exponential family with sigma points, we observe that basically the Bregman divergence is defined some affine term, modulo some affine term, so that if and f and g differ by some affine term, they lead to the same Bregman divergence. So what we're going to do is to choose a sigma point omega in the support, and we're going to take the minus log density, okay? And this is a convex function in our case. And if we express it here, we see that it is the cumulant function, which is a real analytic convex, and here we have an affine term, okay? And by computing the gradient of that, we have this formula, and plugging the fact that this is the Bregman divergence here, we obtain this expression, okay? So for any omega in your support, you can express the KLD as a log density ratio plus some term here. And now we are going to annihilate that term to make it to tend to be zero by choosing some special value for omega. So let's say that we have an exponential family of uni-order, okay? So the natural parameter space is 1. What we need to do is to choose a sigma point omega such that we have T of omega, so the sufficient statistic at omega, which is equal to the gradient or derivative of f for lambda 1 in the natural parameter expression. And if we do that, then we have the Kullback-Leibler divergence, which is expressed as a log density ratio here. Okay. So to illustrate this formula, let's take the relative distribution, which forms some exponential families. We have the natural parameter here, the sufficient statistic here, the derivative here. And what we need to do is to choose omega in order to satisfy this equation, which is this equation here. So we are going to choose omega, which is lambda 1 square root of 2. Then this term becomes 0, and we have the KLD between two relative distribution, which is expressed like that. And we can massage this equation to let it be eta codicile to divergence between the square parameters. So I told you that basically sigma point needs to belong to the support, but actually it's enough to have the sigma to be inside the closed convex cell of the support. So the next slide will take the example of the Poisson family, which is again an exponential family, but with a probability mass function. So it's a discrete random variable. And we are going to replace the expression of the PMF by expression of the PDF here with omega, okay, gamma. And by doing that, what we need to do now is to choose omega such that we can annihilate this term by taking this equality. And let's write it like that. Okay, so we find again the KLD between two Poisson PMF. So when we have multi-order exponential family, the trick is to use not one but S sigma points and to make the average. Okay, by doing the average, we have the Kullback-Leibler divergence, which is expressed by this quantity. And now what we need to do is to make this term equal to 0. So that means that we need to choose our sigma points here, such that the average of the sufficient statistic as the sigma points equals the expectation here of the sufficient statistics for lambda 1. And if we do that, then the KLD can be expressed as the average of a log density ratio. So for example, let's take the multivariate normal distribution. So it's an exponential family of order d plus 3 over 2. And we use 2D sigma points, which is less than the order plus 1 of the family. And we are going to express the KLD between two multivariate normal distribution by choosing our sigma points according to the eigenvalue and eigenvectors of the covariance matrix sigma 1. And if we take this quantity, then we find that we have this relationship here. And we can express the KLD as this formula, okay? And this is exactly an identity with the usual formula for the KLD between two normal distributions, which is a half square Malanobis distance plus a spectral intercolossite distance based on the eigenvalues of this matrix. So just some observation of what we are doing. The usual pipeline is that you're given random samples and you want to estimate, let's say with a maximum likelihood estimator, your parameter. Here you estimate in the moment parameterization given n samples as this quantity by this estimating equation. What the sigma points do is the converse, is that we are given this quantity and we need to find omega in the support so that we have these quantities that match. Okay, so here we go from the samples to the parameter, and here we go from the parameter to the sigma points. So one application of the theorem of expressing the KLD as a average log density ratio is to estimate, it's not to estimate, it's to really characterize the Monte Carlo error in stochastic approximation of the KLD. Okay, we can show that the difference between the real KLD and the true KLD and the estimating Monte Carlo KLD for two density of an exponential family is exactly this quantity, okay? And when the number of samples of your Monte Carlo stochastic integration tend to infinity, this term tends to this one, and then this becomes 0, okay? What we have done for the KLD, we can do it in general for Bregman divergence. So because, as I told you, Bregman divergence are defined modulo some affine term here. So we have some flexibility in choosing vector parameter A. And we can rewrite the Bregman divergence like that, okay? And we make, again, some average weight, non-uniform here. And if we choose our AI so that we have this weighted average, which is equal to this quantity, then the Bregman divergence can be expressed as a weighted difference between the generators here. So there's no gradient in this expression. This is a good thing. And what we can do now is given some query parameter θ2, which belongs to the affine hull of our chosen sigma points here. We compute some barycentric coordinate for θ2 to get the sigma points, and then we express the Bregman divergence as this thing. So there is no explicit use of nabla, but it is used implicitly in the composition of the lambda here to annihilate this term. So if f is very difficult to compute or very time-consuming, what the sigma points can do is pre-compute, and then during query time for for θ2, take the barycentric coordinates and then get this expression where you have those terms that have been pre-computed. So the technique for sigma points can rely on Bregman divergence, and it can also be used for any statistical divergence which amounts for some Bregman divergence. They say that you have the q-divergences between deformed exponential families. In that case, what we take is we take not minus log p theta, but minus the deformed logarithm, and we have this quantity where fq of theta is called the free energy of the deformed exponential family. And we have an extension of our theorem in that case. Here we don't have a log density ratio, but a difference between deformed logarithms. Okay, so the details are inside the paper. And now the constraints to make the remaining terms equal to 0 is to have the sufficient statistic at the sigma points to be equal to this Q expectation. Okay. So to summarize and conclude this work, we have shown that we can choose the generator to be minus log of p theta I for some sigma point, where sigma belongs to the support of the exponential family. And if we choose S sigma points such as this quantity is satisfied, then we can express the KLD as some average log density ratio. And we have shown as one application that we can assess exactly the error in Monte Carlo estimator whenever we use the KLD between two densities of an exponential family. Our technique relies on Bregman divergence and other statistical divergences which are equivalent to Bregman divergence on parameters can be also fitted in this framework. So basically, KLD between the exponential family or Q divergence between Q exponential family or chi divergence between chi exponential family. We have also worked on this modulo affine term equivalence relationship to compute other statistical divergence like the Bhattacharya or Ellinger or alpha divergence between densities belonging to some exponential family without explicitly using the cumulant function. Okay, so the details are reported in this report. Thank you very much for your attention.
Okay, is there any question in the conference? In the room? Sorry. No? So I have a question. Frank, do you hear me?
Yeah, sure.
So your work is kind of remind me something about like quadrature in a numerical computation. Do you think it's possible to do like, it seems to be like Gaussian quadrature, but without any approximating error. So maybe you think it's possible to apply in this kind of problems, or you have some really huge constraints, or maybe the function when you want to compute the integral?
Okay, I think it's a different aspect. You're talking about quadrature and numerical integration.
Yeah.
And here it's a flexibility in choosing the generator of Bregman divergence.
Okay.
Basically, this is a strictly convex generator, but you can define it modulo affine term. And what we had here is just a tricky way of expressing it as a log density ratio. I suspect it has some application in machine learning for other aspects. Now to have overuse of sigma points for other statistical divergence in general, I don't know yet. I think it's a good way to look at the problem to bypass the integral calculation, but how to choose those sigma points then is not so easy. The Bregman identity with KLD is making it explicit in our case, but in general, I don't know.
Yeah, I think it could be computationally easy to compute the sigma points, and maybe it goes back to the same complexity as for a quadrature, a basic quadrature, in terms of computational power, for instance.
Actually, I used to call those points sigma points because in signal processing, when you have Kalman filter, you have the uncentered transform that has been worked out by Julie and his team, and it has a lot of analogy with that. So.
Okay, so thank you very much.
I have a question.
You have a question?
Personal one. Est-ce que tu te connectes à 18h?
It will be 1 a.m. in Japan, so, and I have my children here, so
Okay.
I will see. I cannot guarantee, but I will try.
Okay, okay.
Okay.
I have a question too. What happened if the domain of the mean is not convex? So if your exponential family is not steep in several dimensions, it could be not convex. Do you?
Yes.
Problem?
I think so. Then this